In today's video, we shall look at Heisenberg uncertainty principle, which states that we cannot know both the position and speed of a particle with perfect accuracy. The more we nail down the particle's position, the less we know about its speed and vice versa. Stated mathematically, the uncertainty principle is given by the equation delta x delta p is greater than or equal to h over 4 pi, where delta x is the uncertainty in the particle's position. Delta p, which is the same as delta mv, that is mass times velocity, which is momentum. So delta p is the uncertainty in the particle's momentum. H is Planck's constant. With a value 6.626 times 10 to the power negative 34 kg meter squared per second. Then this is pi with a value 3.1442. So what this means is the more we know about the position, the less we know about the momentum, and vice versa. So we cannot know both at the same time. So this limitation is so small. This limitation is so small for large particles, such as the cricket ball. However, for small particles, such as the photon or an electron, the limitation becomes quite important. So we shall illustrate the cricket ball and an electron. Suppose This is the cliff. There's a ball there, the cricket ball, and this ball is kicked and it's moving at let's say 15 meters per second. So by using the principles of projectile motion, we can predict the position where this ball would fall. But this is not so when a smaller particle such as an electron is used. So suppose the electron is moving at the same speed in this direction, so it may either go straight or go up, or it may change the direction to go down. So here now we have a range. It is not possible to locate the exact motion of the electron, or rather the position. So here we simply use the probability of finding an electron in this region. So applied to the electron, the uncertainty principle implies we cannot know the exact motion of the electron as it moves around the nucleus, as illustrated above. So it is therefore not appropriate to assume that the electron moves around the nucleus in well defined orbits, as illustrated in the Bohr model. So it is practically impossible to know the exact motion of the electron. So according to Bohr, this is the nucleus. Then the electrons are moving around the nucleus in well-defined orbits. So according to this principle, the Heisenberg uncertainty principle, this now contradicts with the Bohr model. Therefore, the Bohr model was discarded. So the quantum model of the electron, the wave mechanics or quantum mechanics, is in no way derived from the Bohr model. So because the Bohr model was found that it could not work for other atoms other than the hydrogen atom. Therefore, it was discarded. But historically, it is important because it helps us to calculate also the energy levels in the hydrogen like atoms. So now we can have an example where we are going to calculate the uncertainty in position for a Bohr and that of an electron, and compare. Example, what is the uncertainty in the position of an electron of an electron mass 9.11 times 10 to the power negative 31 kg, given an uncertainty value of 0.18 meters per second in the velocity of the electron So here now we can calculate the uncertainty in position when the electron is moving at 0.18 meters per second. So using the the Heisenberg uncertainty principle, we have delta x, delta p greater than or equal to h over 4 pi. Then we can make x the subject, delta x the subject. Delta x is greater than or equal to h over delta p 4 pi. Then now we know that 1 joule is equal to 1 kg meter squared per second. So now we know that Planck's constant normally is given in joule per second. So we simply substitute joule by this kg meter squared. Then now we have since it will be kg meter squared second times second, so the times the second, it's second squared. So here we cancel that, then we remain with a second. So in this case the Planck's constant will be 6.626 times 10 to the power negative 34 kg meter squared second over delta p is mv. Our mass is 9.11 times 10 to the power negative 31 kg times 0.18 meters per second, then 4 pi. So we can check our units with the cancel, kg cancels, then meter, second. So we have remained with seconds. So now we can compute Planck's constant, then divide by that 9.11 exponential negative 31 times 0.18 times 4 pi. So this is giving us 0.000032 meters. So this is the uncertainty in the position for an electron. So we can take note. So delta x for an electron is 0.00032 meters. So now let's compare with a Bohr. So here what's going to change is the mass. So we are going to maintain the velocity. So let's change the mass. We know the Bohr is heavier than an electron. So suppose the cricket ball has a mass of 2.0 kilograms moving at that velocity. So we will use the same. Let's calculate the uncertainty in position when the ball here. So we've now changed is the ball of that mass 2 kgs. So here what's going to change is just the mass. So we can change here is 2.0 kilograms. So let's see the uncertainty in position when the mass is increased. So in this case, we can say 2 times 0.18 times 4 pi. It is giving us, we are getting 4.52. So we have 6.626 times 10 to the power negative 34. Then we divide it by 4.52. So we are getting 1.46 times 10 to the power negative 34 meters. So that is the uncertainty in position for the Bohr. So now we can compare to that for an electron. So the delta x for the Bohr is 1.46 times 10 to the power negative 34 meters. So as you can see from the two values, this value for the uncertainty in position, it is practically difficult or impossible to measure that length. It is so small. So that is why it's we have indicated earlier to say that this limitation is so small. For large particles such as a baseball or a cricket ball that is unnoticed. But for smaller, the limitation is quite important. It becomes quite important for smaller particles such as an electron or a baseball, an electron or a photon. So it becomes the limitation is it's quite important for smaller particles, but for larger particles, the limitation is so small, so it is difficult. You cannot measure. It's practically difficult to measure that length. Okay, so also for example, a car is moving at 60, let's say 60 kilometer per hour. 60 kilometer per hour. It is possible to measure the speed, and at the same time locate its position. But this is not so when a smaller particle such as an electron is used. You cannot know both the position and the momentum at the same time. The more you know one, the lesser you know the other. So as the other one increases, then the other one must go down. So normally in our everyday lives, this and Heisenberg uncertainty principle normally just applies to the microscopic world. We deal with very small particles, but for larger particles, the significance of it isn't that much. Okay, so that's how we can solve questions involving the Heisenberg uncertainty principle. So as the more you know about the position, the lesser you know about its momentum. Okay, so in the next tutorial we shall look at the spin quantum number and the Pauli exclusion principle. We shall also look at the alpha-bound principle. We see how we can write the electron configuration of the elements. Thanks for watching.